Cool. Nice, that is really bright. Are you just going to... Oh, you want to take a photo? Oh, lol. Sure. Are they?
Yeah.
Wait, what? It's...
Okay.
Cool. Cool. So it's recording. Can everyone online hear me? Can everyone online? Oh, wait, I need to share the screen. Yeah, sorry about that. Give me 1 second. I need to share the screen. Sorry. Yeah, I just need to share the screen.
Share screen.
There.
Yeah. It's recording.
Yep. Cool. Can everyone online see the screen and hear me? All good? Yes, cool. Hello, my name's Hassan. I'm going to be running your crash course for 3114. Just to give you sort of a general outline of how the crash course will run. So I'm going to go through the papers, last year's paper. I'm going to also obviously provide solutions, but more than just providing solutions, I want to try to break down the theory behind the questions, because fundamentally the theory is far more important than the actual questions. Because the second the question changes slightly from something you might remember, if you don't have the conceptual understanding, you'll find it very difficult to apply it to a different context. And just before I get into the actual exam, just a bit of exam advice itself. Usually when students approach the exam, it's very, very tempting to try and blitz through the exam. Because you might think there's too many questions, I can't waste any time, I can't slow down, I need to keep going. But what often happens in that sense is that you don't spend any time actually appreciating the question itself and understanding the context. So then once you get to part A, part B, part C, and you realize you've made a mistake or you've misread the question, because you're trying to blitz through the exam, you feel like you can't go back, so you keep trying to go forward. But then you make another mistake, and all of a sudden the mistakes are compounding, and you begin to feel very overwhelmed, and you feel very flustered, and then it's basically just downhill from there. So in this exam, there are 3 questions, and if you follow the correct path for every question, which is easier said than done, you will finish the exam with time to spare. Now, the reason I'm mentioning that is because technically we don't want you to blitz through the questions, right? Because in doing that, you continuously send yourself down the wrong path. So my advice is, in terms of your time management, economically speaking, you're much better off spending 1 to 2 minutes reading the question thoroughly, making notes on your exam paper if you have to, rather than wasting 10 minutes trying to go back and find your mistake, right? And then it just turns into a positive feedback loop, pun intended, and you just continuously keep making mistakes, right? So instead of wasting 10 minutes trying to find your mistake, which could have easily been avoided, you're better off spending 1 to 2 minutes actually appreciating the question itself. Now, I'm not saying go slow and meditate the whole time, but I'm suggesting that you go a little faster than normal, but don't try and go 1,000,000 miles per hour. In most of these questions, sometimes the solution is 1 to 2 lines, but you could easily turn that into 20 lines if fully understood the question. Yeah, was there any questions before I get started on the exam as a whole, or should just crack down into the questions? All good? Cool. So, question 1. So this is just a standard sort of mechanical system that you would have seen multiple times. So what we see is that we have one system here, we have another system here, and they're connected by gears on this side. Now, it asks us to find the transfer function of θ2, which is our output, and our torque, which is our input, and it's 8 marks. So there's another 12-mark part later. Now, in these questions, what you're always going to want to do is to reflect one side to the other side, just to make your lives easier. But before even doing that, you need to sort of count the degrees of freedom. Now, in this problem, the way to calculate the degrees of freedom is you hold one of the inertias still. So if I hold this one still, will the other inertia move? Does anyone know? No. Why?
they're directly connected by the gears.
Yeah.
They're like essentially coupled.
Yeah, exactly, right? So because the gear doesn't add any degrees of freedom, right? If this one doesn't move, the gears won't move, and hence this inertial system won't move. So I have 1 degree of freedom and 1 overall equation. So you could reflect it to this side or this side. I'm just going to reflect it from the secondary to the primary. And note that when you reflect things to the primary side, you need to multiply the thing you're reflecting by the destination gear over the source gear. And then you square that. So my destination gear would be N1 and my source gear would be N2. Now, if I were to draw that, sorry, whoops. So, 1 second. Okay, so if I were to draw that, the system would look like, so this is just my primary side. So J1, my damping, like that. So K1, D1, and then I'm going to start to reflect the secondary side. So on the secondary side, I had an inertial system, right? Like so. But now instead of having just J2, I have to multiply that by my reflection coefficient. So sorry, so my source over my destination over my source squared. Same thing for this one, and same thing for this one. So N1 on N2 squared times N1 on N2 squared. That's better. Okay, so now what we notice is that I can sort of simplify this a little further. So I can write this as one whole system because there's only 1 degree of freedom. So this one would just be JEQ. So that's my 2 inertias, a spring, a damping, like so. So K equivalent, D equivalent. And my J equivalent is just going to be J1 plus my other inertia, N1 on N2 squared. My equivalent spring constant will just be K1 plus K2, N1 on N2 squared, and same for my damping. So D1 plus D2, N1 on N2 squared. Now going forward, I don't have to use any of these, right? Don't waste your time writing those. You can just use JEQ, KEQ, DEQ, okay? And now, so don't forget we have our torque force, so our T and our theta, right? And in this case, it's T1, theta1 because we reflected to the primary side. So then my input torque is going to be equal to the sum of my forces. So I'll have theta1 of, sorry, that should be S, theta1 of S squared, JEQ S squared plus DEQ S plus KEQ. Right? But what it asked for was theta2 on T1, right? Currently we have theta1, so I need to use my relation that theta2 on theta1 is equal to N1 on N2, right? Now, you could be asked to derive this thing, or if you forget, and the way you remember is that when each gear turns, regardless of how big the gear is, they have to turn by the same amount. So if I have one gear going that way, turning a distance L1, I have another gear going that way, and that also has to turn a distance L2, which is the same as L1. They will, each gear has a radius, and the theta it turns with, so theta1, theta2. And then, as we mentioned, that they have to turn an equal distance, and then just using the arc length formula, it's R2 theta2, and we use the relation. So we make an assumption that n is approximately 2 pi r. Now, this isn't a bad approximation. We actually design our gears to try and obey this relation. So then when I sub that in, you'll get theta2 on theta1 equals n1 on n2. Okay, so if you're ever asked to derive it or you forget it, just remember that the gears have to turn by the same amount. Okay, so then subbing this in, so I'm just going to make my life easier and call this n. So then you get T1
Sorry,
equals,
the screen share has stopped online.
oh, the screen share has stopped. Oh, my
Yeah,
bad. Lol. So sorry. Let me reshare the screen. Sorry about that. Sorry, I was not looking at the chat. Cool.
Could you
Cool.
repeat the
Can we
question?
see the screen now? Can we see the screen now? All good? Yes, okay, and you can hear me clearly, not cutting out? Cool. Okay, so just to sort of recap really quickly, I just reflected everything like this. So I wrote it as one system. And then I wrote it as one whole system, right? I'm not sure exactly where it cut off, but that's what we've essentially gotten up to. And then I've just written my force equation. So my input torque is equal to my other forces applied. And then I sort of just derived the gear relationship, which was that the gears have to travel an equal length. So length 1 equals length 2. No, as in you can't see the screen? Okay. Does someone mind joining the teams just in case I mess something up? Okay, it works, cool. Yeah, so then that's where I'm up to. So just subbing in theta 2, so that'll be T1 equals N1 on N2, N1 on N2 theta 2, JEQS squared plus DEQS plus KEQ. So then I can just say, therefore, my input torque over my, my output over my input. So my output over my input will just be N1 on N2 over S squared plus DEQ S plus KEQ, JEQ. But what I'm going to do is I'm going to write this in monic form. So I'm going to divide everything by JEQ. So we'll have on JEQ, on JEQ, on JEQ. And that's pretty much the answer. Any questions? Did I mess that up? Possibly. I don't think so. Is it? Did I make a mistake? Theta 1 equals, yeah, it should be N2 on N1, right? Yeah. So that should be N2 on N1, my apologies. So that's fine. So that one there should be N2 on N1. Cool. Now, moving to the next question. So the next question, essentially what we do is we apply a step response to our system. So the time response of the system theta 2 to an input step torque of T1 equals 3. So essentially our input is T1 equals 3 on S. It's just a step input. And we're given some gear ratios, N1 equals 1, N2 equals 5. And so we're given J1, D1, K1, oh no, sorry, my bad. We're given N1, N2, and we're given the secondary side parameters as well. So we're given all of these. And what we're asked to find, is K1, D1, J1, right? That's what we're asked to find. And we're given the step response of this system. So this would be our output theta 2, right? So that's our output theta 2 step response. And we're given some measurement data. So what we're essentially given is a response that looks like this. So we have, so generally for an underdamped response or just a general response, it'll take something of the shape like this. It'll approach some steady state value. We call that YSS. And one really important thing to mention is that you might have a desired steady state value that you want, but in reality, it might reach something else. If a question gives you a desired value and an actual value, you use the actual value because that's what happened in reality, okay? Another thing we're usually interested in is the first peak. We're interested in the peak time. We're also interested in the overshoot, so percentage overshoot, right? And those are usually nice and easy to spot on the graph. And that's still a part of our transient response. So our transient response is this sort of growing part, and then our steady state would be this part. So what we're also interested in for our steady state response, for our transient, is the rise time, which is defined as 10%, 10% of the final value to 90% of the final value. So how long it takes to go between 10% to 90%, we call that our rise time. And we're also usually interested in the settling time. So somewhere here, that's just how long it takes to get within 98% of the steady state value, oscillating within. So if we go look at our graph, we're given a lot of things, right? So we're given the overshoot and the time at which occurs, so our overshoot and peak time. We're given our settling time, and we're also given our steady state value. So if I write that down, so we are given a percentage overshoot of, I think it was 12.2%. 12.2%. What else are we given? We're given peak time, 3.15 seconds. Peak time, settling time as 4.84 seconds. And we are given that the steady state value it reaches is 0.708. Now, you have to be careful here in the sense that it's almost like we're given too much information. I don't really need all of this information, and I'll show you why. But first, let's get our actual response. So let's get this down. Let's copy that. And let's paste it here. So this is what we're working with, right? So T2 equals this. So our transfer function, let's say G of S, equals this. Now it's sort of, how do I approach this question? So anytime you're given overshoot and these sort of parameters, you're immediately thinking, I need my desired characteristic equation. So ideally, what you'd want this equation to look like is some gain over S squared plus 2 zeta omega ns plus omega n squared. And we call this thing our desired characteristic equation, because if I know zeta and I know omega n, I can immediately find the overshoot, peak time, settling time, basically everything I want to know about my system. And I can find these formulas. I can find zeta and omega n using these, and also using your formula sheet. So using your formula sheet. So you'll be given a Laplace table, but more importantly, you'll be given these parameters, right? So overshoot, for overshoot, you're always going to use this formula usually to find zeta, because it's just in terms of zeta. But then you have your choice of using peak time or settling time, right? Which one should I choose? Settling time? Which one? So I'll just mention that whatever you use, your answer won't be incorrect, but practically speaking, one is more, some answers are more correct than others. Which ones did we make an approximation for? So this one is known exactly, right? Because that's just to find the peak, you just take the derivative, right? So that formula is known exactly. Which formulas were approximations? The settling time, right? So the settling time is an approximation. The rise time is an even worse approximation. So if you can avoid using the settling time and the rise time, you should. Or if you're asked which one is more accurate, your peak time and your overshoot are going to be the most accurate because they're easy to find, right? So I'm going to go with this formula and this formula. So, whoops, there we go. So my zeta would be, hold on. So I have working out next to me, so I don't actually have to do the calculations. Let's see. Okay, so my zeta would be ln minus ln percentage overshoot on 100 over square root pi squared plus ln squared percentage overshoot on 100. And this is the last time I'm going to write this, right? You don't have to write this. It's too long. You're going to waste your time. It's given in the formula sheet as well. Okay, so then when you sub in the overshoot of 12.2%, you get 0.556. Then the next formula I'm going to use is the other one, which was for the peak time, and this was pi on omega n square root 1 minus zeta squared. And when you rearrange this for omega n, you get omega n equals 1.2. Okay, so now I have my omega n and my zeta parameters. So, 1 second. Okay, so I have my parameters. Now the goal is, so let me move this slightly down. I want to equate my coefficients. So I want to equate this coefficient with this coefficient and this coefficient with that coefficient, right? But before I even go there, you'll notice I'm given the steady state value. Now, the steady state value is usually always the easiest value to work with because the steady state value, right, we just use the final volume theorem for, right? And for that, I just need to set S equals 0 to things, right? So the first thing to do is to look at your equation and to see if I'll get anything out of that, or I'm wasting my time. So if I set S equal to 0 in my transfer function, that goes, and then I'm left with this on this. So that could tell me something, right? So maybe the first equation I should start with is my steady state, because it gives me something, and really easily as well, right? So what I'll say is that my steady state, so in this case it's theta 2, so theta 2 steady state is equal to the limit of S approaches 0 of S theta 2 S, right? And this thing is just S times my transfer function, so G of S, times my input, which was the torque. Now recall that this one was 3 on S, right? That one was 3 on S. So then that S and that S will cancel. And so I'm just left with the limit as S approaches 0 of 3 G of S. Okay? And so then I set 0, 0, and then I'm left with, so then this would just be N2 on N1. Actually, I think it should be N1 on N2. Having a look at my working. Yeah, because then you reverse the order here, but then you have to reverse it back when you flip the fraction. So yep, so that one should be N1 on N2. N1 on N2. Okay. And now if we go back, so just fixing that, N1 on N2. Then I'll get, so what will happen is that'll go to 0, that'll go to 0. This JEQ will cancel with that JEQ. So I'm just left with the gear ratio over KEQ. And this is really good because the gear ratio is known, so I can find KEQ, right? So then from this I can say, that KEQ equals my gear ratio, which is, what were the numbers? I think it was 1 and 5. Yep, so my gear ratio was 1 on 5. I also can't forget my 3 times. So 3 times 1 on 5 over the steady state value, which was given as 0.708. And this comes out to 0.799. Is that okay so far? Any questions? Cool. So now with KEQ, recall that KEQ equals K1 plus K2, my gear ratio, which was just N1 on N2 squared. So from this equation, I can find my K1, right? Because that's what was missing. I had these secondary side parameters, but I didn't have the primary side parameters. So I can just say, therefore, K1 equals KEQ minus K1 minus KEQ minus K2 N1 on N2 squared. And when you sub in all the parameters we're given, plus the KEQ, you get 0, sorry, this one misreading my own writing. 0.847, and this one was 0.8. Okay, so we found K1. That's all good. Now we need to go back to this equation where we were equating coefficients, right? Right, so if I equate coefficients, now don't waste your time rewriting the top numerator as omega n squared because really who cares what's happening on the numerator, right? Because what I care about is my poles. If I change things on the numerator, it's just going to scale the whole transfer function, but it's not going to change my pole locations. So don't waste your time, just write K. So then from the first one, I get DEQ on JEQ equals 2 zeta omega n, right? And then from my other one, I get KEQ on JEQ equals omega n squared, right? So just equating coefficients of the denominator with my characteristic equation. And then from this I can say, therefore, oh, actually let's start with the bottom one, right? Because from the bottom one I have KEQ. I know what KEQ is. So I can say, therefore, JEQ equals KEQ on omega n squared, both of which are known, right? So when you sub in those values, you get, where is it? 0.588. Okay, does that make sense? And then for this one, I can say, therefore, DEQ equals 2 zeta omega n times JEQ. And this is equal to, so using the value I just got plus my zeta and omega n, this gives you 0.784, right? Now basically I've done all the hard work because DEQ was just D1 plus D2 N1 on N2 squared, right? It was just that. So then from this one, I can say, I can just say D1, so rearrange for D1, and you get 0.7, and then you do the same thing for JEQ equals J1 plus J2 N1 on N2 squared. J1 equals 0.5. And that's it. Okay, so we found D1, G1, and K1. And these are the parameters which will give me my desired overshoot characteristics that we saw in that response, as well as peak time and settling time and whatnot. And I just really want to emphasize the importance of having a structure to your answers. It's easier said than done in an exam, but you need to go in with the mindset that you are going to make a mistake, right? It's easy to think that, you've seen a question before, you won't make a mistake, but just, it's important not to be in denial and recognize that you will make a mistake. And that's okay. But you need to be able to go back and look for your mistake. And that's very difficult if your question's all over the place. Okay? Was there any questions on this question as a whole? So this was question 1. All good? Up back. Any questions online? Do we need to write units for these? I can never remember them. No, don't worry about it. No one remembers the units. I don't think I do either. Yeah, so you don't need to write units. Okay? Yeah, what's up? This one was 12 marks.
Sorry, 12 marks.
Yeah.
And obviously the answers are going to be like message. But what would be like sort of the marking breakdown?
So you're not marked for your final answer. If I'm looking at this, there's only really 1 mark for the final answer. So you'd be given, so just having a look at the marks I have here, you'd be given 2 marks for doing this, right? You'd be given, so it's 12 marks overall. You'll be given 1 mark just for writing this, right? So there's 12 marks, so it's a lot to go through. But essentially, you're given your marking for your working out, right? So don't stress about the final answer too much, okay? I'm not in saying that. Try to get the correct answer, but don't stress that you're going to get 0 if you don't, okay? Cool. Any other does it matter which side we reflect? No. You should get the same answer when you in your final monic form equation. So either side you reflect to is completely okay. Cool. Any other questions? All good? Cool. Okay, so question 2. Consider the closed loop system shown in figure 2. So we have just our standard forward loop and feedback path, right? And the first question says, find the closed loop transfer function T of S equals Y of S on R of S. Okay, so let's do that. So the quickest way to do these equations is to remember our quick form, right? So you can go through and you can write what the signal is here, what the signal is there, and go down the long path. And keep in mind, you may need to do that if you're given an unfamiliar form. Okay, so if you're given something that looks maybe like this has its own feedback or something, right? Some crazy thing like that, then you're going to have to sit there and write out all the signals going between each branch. So you can only use this form when you have a known equation. Okay. So the known form is just that is the forward elements, so forward elements, over 1 plus the loop elements. Okay? And then, so my forward elements comprise of this stuff. So I have GP, G of S, over 1 plus, so my loop elements would be everything here. So 1 plus G, H of S. Okay? And then just writing what this is. So my GP is just N, my G is 1 on S plus 1, S plus 3, over 1 plus K, S plus A, over S plus 1, S plus 3. Okay, so just rewriting what they are exactly. And then to quickly multiply this and not waste too much time, just look for the fraction that has the most terms in it, right? So this one and this one have the most terms, so I'm going to multiply the top and bottom by them. Okay, so then this I can just say, yeah, so this one I can just say n over S plus 1, S plus 3, plus K, S plus A. Okay, and it asked me specifically to find the transfer function, so I need to write it in a nice way. And the nice way is monic form. Okay, so in this case, the monic form will sort of drop out. Maybe let me put my... Okay, so the monic form will just drop out. So S squared plus 4S plus 3 plus KS plus KA. And then you want to group this into the obviously common terms. So S squared, S, 4 plus K plus 3 plus KA. And that's my transfer function. Was there any questions on that? All good, just finding the transfer function. We've done that heaps of times. It's actually, cool. Next question. Determine the number of zeros and poles in both the open loop and closed loop transfer function. Now, this question is a little tricky in the sense that I think like 90% of students got 1 out of 2 for this. So you have to be really careful in the sense of what it means by open loop. Okay, so in this question, we're given the closed loop system. Now, practically speaking, you might think back to your labs that H of S usually refers to some sort of center. And so that when we have our open loop system, we're not including this because we don't have that feedback. But I'm told nothing about the system. There's no context, there's no nothing. So we can't assume that this wouldn't also be a part of our open loop system, right? Because when I go from closed loop to open loop, I want to keep all the elements there so that when I go back, I can also go back to closed loop, right? Keeping all the elements there. So usually what students will do is they'll assume the open loop is this, right? So they'll get rid of this entirely, but what you actually have to do is you have to cut the feedback loop there after all the elements, okay? So you'd cut the loop here, right? So then my open loop transfer function will look like, and another key point is that I think Arash mentioned this, is that the output isn't always, this might not always be the output, right? That might be inaccessible. Maybe the output here, right? Again, there's no context. We just have to keep everything in our system when we switch between open loop and closed loop, right? We don't know what this is being used for, okay? So then my open loop system is just going to be G of S, H of S, and then my output there, okay? And then I can say my open loop transfer function is going to be, T open loop is going to be N times G of S times H of S, which is equal to N KS plus A over S plus 1, S plus 3. And I don't need to bother with simplifying this because all it asks for is the number of zeros and poles. From this one, we can see that the number of zeros is equal to 1, and the number of poles is going to be 2. Okay. And then from our closed loop system, right, we know that so if we go back, there's no zeros on top, but there's a second order system on the bottom, so we know that there's going to be 2 poles. Okay. So then this one would be, so zeros equals 0, poles equals 2. So when we've closed the system, we get rid of the 0, which is usually desirable. Okay. Was there any questions on this? All good? Online? All good? Cool. So now this one's nice. This one's not too bad. So no tricks with this one. Just determine the constant gain of n such that the DC gain of the closed loop system is 1. So for this one, we just need to get our transfer function once again. So this one. Right, so this is our transfer function. And the DC gain will just be when T of S equals 0, right? And so what we'll have is we'll have n over, so that'll disappear because it's when the frequency is 0. So then we'll have n on 3 plus Ka, and we're told that we want the DC gain to equal 1, right? So then I just need to multiply across, and I have n equals 3 plus Ka. Cool. Any questions? Oh, yeah. Oh my God. There we go. I saw your confused face. All good? Cool. Now, calculate K and A for percentage overshoot. So the only difference with this question is now we're given a range. So we're not given an exact value for overshoot. We're saying I want it to be 5% or lower. So for this one, you have to be a little careful. So we're given that the percentage overshoot should be less than or equal to 5%. Now we have to think, what should zeta be, right? So if we go look at our formula for zeta, where is it? Very complicated and very ugly, right? So if you try to calculate the inequality of what zeta should be from this, it's not so straightforward, right? Unless I'm missing something, I don't think it's intuitive, right? So I like to think of it in a better way. So I like to think about the relationship between overshoot and zeta. So your 3 types of responses are, you might have underdamping, you might also have critically damped. That is weird. There we go. That's better. Or you might have overdamped. Now, critically damped is when there is just enough damping to crush the oscillations. Overdamped is when there's too much damping, and then underdamped is when there's not enough damping. So what do we notice as the relationship? Right? What do you think zeta should be? Greater than or equal to, or less than or equal to? Less than 1? So if my zeta is less than 1, that would cause greater oscillations. Right? So if I reduce my zeta, I reduce the damping factor. So now it becomes more underdamped. So that's sort of the direction I don't want to go in, right? I want to go in the other direction. I want to increase my damping so that I'm less than 5% overshoot. So what I would need is I'd need my zeta to be greater than or equal to some value. Does that make any sense? I just prefer thinking of it this way, other than trying to look at the equation, right? So I want 5% damping. I'm happy with 5% damping, but if I have to settle for less overshoot, then I need to crush the oscillations even more. Okay, and for that I need greater damping. So this here would be like zeta much less than 1. Okay, and then you do that. Oh, I need to find that. You do that, and you get that zeta. Is that 0.69? Yep. Okay, and then the next one is TS, settling time, but that one's nice and easy, right? That's just the formula is just zeta omega n, right? So this inequality is not too hard to work out because this one just needs to be less than or equal to 1.2, Therefore, omega n is greater than or equal to 4 on 1.2 zeta, right? And then, so then this one is, here's the value, 4.83. Okay? Does that make sense, everyone? Cool. But we have to take this one step further, and then it says calculate K and A. So what I'm going to need is my characteristic equation. And again, I don't need to keep rewriting the transfer function because all I care about is the poles. I care about this thing, right? Because the poles are what determine my system's response. So then I'm going to equate this to my characteristic or my desired equation because I know everything about this system, right? I know the zeta, I know the zeta and I know the omega n. So then all that's left to do is just equate coefficients, right? That goes to that. That goes to that. Okay. So then from this, so from the first equating, we see that 4 plus k is equal to 2 zeta omega n. And from the second one, we see that 3 plus ka is equal to omega n squared. Okay. And then, so then we can say, so from the first one, so we have to start with the first one because that is only k, rather when the second one has k and a. So we say, therefore, k equals 2 zeta omega n minus 4, which is equal to 2.67. And then in this one, we say, therefore, a equals omega n squared minus 3 on k. And this one is 7.614. And that's that. Okay, so yeah.
So do we need to also write these K and A values for this question? So you like
Oh, sorry.
the lower bounds of what well, the upper bound, the lower bound for zeta, and then the lower bound for omega n.
Yeah, so strictly speaking, you're supposed to write these as inequalities, right? So you're right. So in this sense, instead of having an inequality, since zeta and omega n must be greater than some value, you'd write k greater than or equal to, strictly speaking. In the solutions, Arash has just written equals. So it's probably okay if you don't try and work out the inequalities, as long as you acknowledge that the inequality is there, right? That zeta inequality. Okay? Was there any questions? All good? Online? All good? Okay, let's move on. So this one is quite long, if I'm being honest. So I'm going to work you through how I would do this one and how to avoid mistakes. So this one says, derive the response of the closed-loop system to a unit step reference signal for t greater than 0. So we are going to need our transfer function, which was our transfer function. Where was it? There it is. Okay. So our transfer function was this, right? So this was our g of s. I don't know what we called it. I think h of s. So this was y of s on r of s. Okay. Now I'm just going to sub in all my numbers, and this thing is just 1 on s, right? It's just a step input. So I'm going to write this as y of s equals n, and I'm going to sub in the k and a we found above, and this will give me s squared plus 6.67s plus 23.33. Okay. Now, obviously, we're going to need partial fractions, but that's only half the story because I have to somehow deal with this, right? The type of partial fractions I do is determined by how I can break up this quadratic, right? So, and the quickest way to figure that out is to quickly work out the discriminant. Okay, so if I calculate the discriminant of this thing, right? So, so if the discriminant is say equal to 0, that means I have 2 critical roots, right? So I have a double root. So then I have 2 same roots. If the discriminant is greater than 0, I have 2 roots, 2 real roots. So in these cases, they're real. And if I have the discriminant less than 0, I have 2 complex roots. And again, how you break up the partial fraction into partial fractions is going to be dependent on this. Now, does anyone actually have a calculator? I haven't calculated the discriminant of this. Yeah. So if you do, so your discriminant is just b squared minus 4ac, right? Something you can quickly do on a calculator. It should be less than 0. Yep. So it's less than 0, which means I have 2 complex roots, which is possibly the most annoying case, right? Because I can't break these up into roots, but I can do something else. So one thing I can do very quickly is I can just say a on s, so that's that first root, plus bs plus c over s squared plus 6.67s plus 23.33. Now, this thing here, because I don't have real roots, my only other option is to complete the square, okay? Because it can't be broken down into perfect roots. So I'm going to complete the square on this one. So I'm going to say s squared plus 6.67s. Let me make some more room. Yep, s squared plus 6.67s, and then plus 6.67 on 2 squared. So to complete the square, you just basically take b, you divide it by 2, and you square it, and you also subtract that away to complete the square, okay? So that's going to be my square, but I'm also going to have a remainder. And that remainder is going to be that thing I added, so 6.67 on 2 squared, plus 23.33. Okay? And then, so then what this gives me is a perfect square. So s plus, and 6.67 on 2 is 3.34, I think. Yep, 3.34 squared. And then my remainder will just be plus 12.21. Okay? So just sort of tackling everything I need on one page. So now it's crystal clear what the goal is, what the path forward is. Now, what I need to do is I need to work out the partial fractions. So I need to make this denominator and this denominator the same so that I can cancel them on both sides. And look, you could use the residue theorem, but really there's no point wasting my time because I can't apply the residue theorem here. Maybe I can get one term out of it, but either way, I'm gonna have to equate coefficients. Okay, so there's no point wasting my time there. So what I'll do is, so then from this you get that, what was n? So n was 23.33. So that was 0.33. So then I get 23.33 equals a s squared plus 6.67s plus 23.33 plus b s plus c times s. And of course on this side it's like you have 0s squared plus 0s plus that. So on this side I'm going to bunch everything up in terms of the s squared components. So that'll be a plus b plus s 6.67a plus c plus 23.33a, right? Now it's just a matter of equating coefficients on the left-hand side and the right-hand side. I'm going to skip the details, but you end up with nice answers, right? You end up with a equals 1, b equals 1, b equals minus 1, and c equals minus 6.67. Okay. And then, so then our final response overall will look like y of s equals 1 on s minus s plus 6.67 over, and then I'm going to use my factorized form, the one I completed the square for, s plus 3.34 squared plus 12.21. Okay. Now I need to think that I need it in the time domain, so I'm going to have to take the inverse Laplace. Now you have so the way I approach this is firstly recognizing what it looks like from a common pair that we know of. So if I go look at our formula sheet, it looks something like this, right? We have an s on top, and we also have an s squared plus omega squared. But it's not exactly what we want, right? What we had in our case was s plus a over s plus a squared plus omega squared, right? That's what our case looked like. So what we're going to have to do is to use another property, and it's this one. So we're going to have to combine properties, right? So if I multiply this side by an exponential, e to the minus at, it's like a frequency shift, right? And that's exactly what I need, because what I need is that s goes to s plus a instead, right? So then this will give me on this side, it'll give me this thing there, right? So this whole thing will give me that instead, right? It's the same property, but now it's been shifted to s plus a, okay? Now if we go back, was it this question? Yep. If we go back, now Now we notice that it almost looks like that. It's so close, right? We had s plus a, but we want s plus a on top. The quickest way to do this is to just make it look like what you want and deal with the consequences after. Okay? So I'm going to take this one here, right? And don't rewrite the thing every time. Just target the one you want to. Okay? Target the part of the transfer function you're interested in. So then this one I can rewrite as, so s plus 3.34 over, and then I'm going to rewrite this as the square root of 12.21 squared, because we had omega n squared there. So I just took the square root and squared it. It's the same thing pretty much, right? And now this looks like what I want, but to get there, I had to take away something from 6.67. So I'm going to have a remainder, and that remainder is 3.33, right? Or let's just say 3.34. Right? So now this one we know. This one we know, right? If I take the inverse Laplace of this one, right? It was e to the minus 3.34 t, because that was our scaling, right? 3.34 was what we scaled by. And then I'm going to have my cosine, and then this thing in here determines my frequency. So square root of 12.21 t. Okay? So that one's dealt with. Now we have to deal with this one. And if we go look at our formula sheet, again, this one looks really close to what we have, except that I need to scale it. Right? So I need to put e to the minus at here, so that this one looks like omega over s plus a squared plus omega squared. Right? Now this one looks much more like what we had. So then I go back to question 1, and and then so I want to solve this one. So this one I need to rewrite it in the form I want, right? I want what's here to look exactly like this. So I'll do that first. So I'll rewrite the top as square root of 12.21 over s plus 3.34 squared plus square root of 12.21 squared. But again, I have to fix what I did, right? To make it look like. So I'm going to divide by square root of 12.21. So it's as if I did nothing. And then I'm going to put on top 3.34, right? So that's what I had, but I've just pulled it outside. And then this thing we know the Laplace of, right? This has an inverse Laplace of, so I'm going to have my factor on the outside. So this factor ends up being 0.96 sine, so we have our exponential, so e to the minus 3.34 t sine of square root of 12.21 t. Okay, and that's pretty much all done, right? So what I did is I made it look like what I wanted to first, then I fixed the problem later, rather than the other way around. That's just the easiest way to solve it, okay? And then don't forget, we also have this one here, right? When you take the Laplace of this one, it's just going to be like a step function, so u of t, or just 1, whatever. Technically, you're supposed to put a step function next to all of them, but I'm just going to write t greater than 0 at the end of my answer. Same thing. But you have to be careful. If some of your answers are time scaled, you can't skip the step function, because it's like each part of that function operates on a different schedule, right? So one will turn on at t equals 0, but one might turn on at t equals 5. And the step function encapsulates that. So you need to be careful. In this case, I don't have any time scaling. I had frequency scaling, but no time scaling. So then my final answer will be y of t equals 1 minus e to the minus 3.34 t cos of 3.5 t plus 0.96 sine 3.5 t. T greater than or equal to 0. It's a bit of a workout, but any questions? Online? In here? Any questions? Everyone's okay? So that was the last part of this question. Again, it was quite a long process, but it's important to stay focused and stay organized. So little tricks like quickly checking the determinant will very quickly tell you which way you have to go to, rather than trying to find the poles first. Okay? And that's question 2. Now, this is the biggest question in the exam, right? Now, so this is to do with state space, This one has quite a few tricky questions in it though. So just quickly before I go into this, I'm going to explain sort of the theory behind this, because this is sort of an application of that theory in a different context to what you've seen in the lecture notes, okay? So let's just ignore this for now. So let's say for argument's sake, I had some system plus 3x of t plus x of t equals some input, right? You might have derived this from some mechanical system or whatnot. That's just some equation. Instead of writing in the Laplace domain, we've written it in the time domain, okay? And then for state space, I want to be able to control the state variables instead, right? So the state variables in this case would be my position and my velocity. I could also do my acceleration, but then it becomes redundant. I almost have too many state variables, right? I only need at most 2 to describe my system, okay? So I'm going to rewrite, so I'm going to designate this as say x1, x2, right? So then x1 equals x of t, x2 equals x, the derivative, so the velocity. Then what I can do is I can differentiate this again because I want to be able to get to my acceleration, right? So the derivative of x1 is going to be, it's the derivative of this, which we've already defined as x2. And then I'm going to differentiate this side, so x double dot, x2 dot, and then that's just my acceleration because I add another derivative. That's just my acceleration. So then I'm going to rearrange this as u of t minus, so I'm just going to take this and I'm going to move it to that side, okay? So then minus x1 plus 3x2, okay? So all I've done is I've just written my equation in state variable, I've sort of defined state variables and I've got it and I've obtained my acceleration in terms of state variables, okay? So then what we do is we write this as x1 dot x2 dot, right? Because these are enough to describe my whole system. I don't need anything else, right? So my x1 was just x2, and my x2 dot, which represents my acceleration, was minus x1 plus 3x2 plus u of t, right? Okay, but we want to write this in sort of a matrix form. So the next thing I do is I rewrite it in terms of matrices. So x1 and x2, right? Cool. X1 and x2. So for this, then I'd have 0 x1 and I'd have 1 x2. And for the bottom, I'd have minus 1 x1, right? And then I'd have 3 x2, right? So all I've done is I've just rewritten it in sort of a matrix vector form. Oh yeah, my bad. Minus 3. Thank you. And I also have my input, but I'm going to take that out. Right, so I'm going to write this as u of t. And then, so it's not being added to my first row. It's being added to my second row. Okay? So this is essentially the state variable form. Now, we give everything labels, right? We label this matrix here as A. We label this vector of our state variables as just x of t. And then we label the term which controls the input as b. And then obviously this one is just x of t, the derivative. Okay? Now, what you'll notice is that A seems to be the most important matrix. We expect A to sort of encapsulate our whole system, right? Our characteristic system, right? And now the question is, what do we do with this? So we have x of t equals ax of t plus b u of t. Okay? Was any questions regarding any of this before I keep going? All good? Online? All good? Cool. Online, you can still hear me, right? Just double checking. Please say yes. Can you check? Yep, okay, all good. Thumbs up. Thank you. Just got scared for a second. Okay, cool. Now what I want though is I want to be able to sort of understand the system a little better, right? So what my goal is Oh, also, one thing I forgot to mention is that you could also have an output of state variables, right? So I might just choose that y of t. So my output, let's just say it's going to be some combination of my state variables, right? Some combination of my state variables. Let's just say it's just the first state variable, whatever. It's arbitrary at this point, because I'm just going to call this the matrix C, and then that's our matrix X of t. Okay. So then I also have y of t equals c x of t. Okay. Now the goal is I want to understand the system as a transfer function. I want to understand how this relates to my transfer function. So I need to try and write this as a transfer function. So the goal is I want to rewrite this as y of s on u of s, because u of s was my input and y of s was my output. Okay. And then to do that, I need to go into the Laplace domain. So we're going to take this and we're going to go into the Laplace domain, both of these, right? So I'm going to rewrite this as s x of s. The s is because it's a derivative. And this is going to equal to a x of s plus b u of s. And then on this side, I'll have y of s equals c x of s. Okay. And then I need to get rid of x of s. So I'm going to rearrange this for x of s. But you have to be careful that these are matrices. So whether you multiply something to the left or to the right matters, right? Because it's not commutative. So I'm going to rewrite this as si minus a. And x of s is on the right on this side and is on the right on this side. So I put it to the right there. Equals b u of s, right? And then I'm going to move this to the other side by taking the inverse of it on the left on both sides of the equation. So I'm going to rewrite this as x of s equals si minus a inverse b u of s. Okay. And then basically my job is done in the sense that I just need to take this thing and I need to sub it in there. So let's do that. So then I get y of s equals c si minus a inverse b u of s, right? And this thing here was x. Okay. And then I can take this again and I can rewrite this as y of s on u of s equals c si minus a inverse b. Now, why this was important, so this doesn't look very much like s. That looks like s. So why this was important was because, well, it's not so important yet and it's not so obvious what we can derive from this. What we can note that, sort of as an aside, is we note that for a 2x2 matrix, right, the way we solve for the inverse, let's just say this is the matrix Z, is we write this as 1 on the determinant of Z, and then we switch the diagonal, so we write this as dA and minus B minus C. That's just the formula for a 2x2 matrix. But what's more interesting is that we call this thing the adjunct of Z. Now, the terminology is not too important, but essentially it's a matrix, okay? So then I can rewrite this as C, the adjunct of the matrix over its determinant, B. So that's this thing here. Now, what we notice is that the determinant of Z, right, that's the determinant of Si minus A. We notice that it's on our denominator of our transfer function, right? This, and this, they're just matrices which will give me something in the numerator when I multiply them. But this is in my denominator. So thinking back to transfer functions, it represents my characteristic equation, right? So what I can say is that the eigenvalues of my matrix will give me my will give me my poles of transfer function. Okay, so that's what we need to answer the question. Was there any questions? Yes. Oh, yeah, but you're going to need to do a similar derivation in the question. Yeah. So you look, if it just says find the eigenvalues, just find them, or find the poles, just do it. Oh, yeah. Look, this is not to answer the specific question. This was more notes. Yeah. So but you need this sort of background to answer the question. Okay. So now let's go to the actual question. So consider the dynamic model of a system given below in state space form. So we're given 3 equations, and we don't have to actually do the state space sort of derivation. It's given to us. So I'm just going to, like I did before, I'm just going to rewrite x1 dot, x2 dot, x2 dot. That's equal to, so x1 is just x2, and x2 dot is minus 2x1 minus alpha x2 plus 2u, just rewriting it exactly like here. And then this gives me, so then I'm going to rewrite it in terms of matrices, right? So I'm going to rewrite it as sort of a vector of x1 and x2. And so I have 0x1, 1x2. Here I'll have minus 2x1 minus alpha x2. And then I'll also have an input at the end. So 0, 1. Okay. And then like we did before, I can say that that is my matrix A, that is x of t, and that is B. Okay. Now the system says find the eigenvalues of the system for a range of values of alpha. The system is overdamped, critically damped, and underdamped. Now this one is slightly tricky if you're not paying attention. And I'll get to why in a second. But okay, so how do I do this? What did we just discover? What do I need to find for my eigenvalues? Which matrix is the interesting one? A, right? So I need to just I need to find. So what I need to do is I need to calculate what SI minus A is. So SI minus A, so we're going to have to take the determinant of SI minus A, right? And this is going to be S, so S 0, 0 minus, my A matrix was 0, 1 minus 2 minus alpha. And this is equal to S minus 1. If I make a mistake with any of this, let me know, because I have work solutions, but I'm not really looking at them. S minus 1, 2, and then S plus alpha. Right, so then just finding the determinant of this. So S plus alpha minus 2. So I'll have S squared plus alpha S plus 2. Now the question asks for what values of alpha. So that's going to be dependent on our pole locations, right? Remember, as we discussed when we're finding the response, the type of response we have is dependent on the discriminant, right? So if I were to find, say, S12, I would say it's minus alpha plus or minus the square root of alpha squared minus 8 over 2. Okay? Now, for an underdamped system, my poles lie there, right? I have 2 complex poles, underdamped. So this would be my sigma axis, that's my J omega. So, and then the next one after that is critically damped. So I have 2 poles there. So you notice that the sigma axis, it lies on the sigma axis because there's no damping. There's no oscillations, right? Because the y-axis represents the oscillations. So it's just enough to kill the oscillations, okay? And then overdamped is two roots somewhere there, right? Also on the axis. So if I start with, well, the easiest one would be critically damped. So that would be, so alpha squared minus 8 equals 0. Therefore, alpha equals plus or minus 2 root 2. But who can tell me what I've missed? Someone know what I've missed? Yeah, exactly, right? So if I look at my transfer function, right? So alpha also appears in the real part of the poles. So if alpha is, say, negative, if alpha is negative, then the real part of my poles becomes positive. So then my poles show up on the right-hand side of the plane. So I need to disregard the negative solution and write it as plus. Okay? Now for the next ones, it's also just routine. So we have alpha squared minus 8. So for underdamped, the discriminant has to be less than 0. For overdamped, the discriminant has to be greater than 0. Now in both these cases, we have an inequality. Maybe you know a good mathematical way to solve it. I like to do it graphically. So what I'm going to do is I'm going to plot y equals alpha squared minus 8 as a function of alpha. Oh, alpha, right? So that's going to look something like this. And this point here is going to be minus 8, and then these will be the roots, 2 root 2. So now all I need to think is, for when is y less than 0, right? So when is this graph less than 0? And that would just be here. But which region do I not include? This one, right? I don't include this one because that's where alpha is less than 0, and hence the thing is stable, unstable. So I'm just going to have that region there. So then for this one, or wrong color, that one there. So I have alpha. So I have a range, right? So alpha has to be greater than 0 and less than 2 root 2. Okay. And then for this one, it's just when it's greater, and that's just going to be this region, excluding the left-hand region. So then this will give me alpha greater than 2 root 2. Okay. Was there any questions? All good? Online? All good? Okay. All right, let's move on to the next question. So this one's quite a long one. Find the state transition matrix for the range of alpha that makes the system critically damped. Now, this question could be 10 times longer if you don't approach it right. So what it mentioned was that alpha is critically damped, which we decided was 2 root 2. Okay. So for alpha, 2 root 2, so our state transition matrix, so the very next question actually asks what the state transition matrix means. So I'll wait till then before I talk about what it means. Let's just talk about how to find it for now. Okay. Oops. Sorry. Okay. Now, so the state transition matrix is given by the inverse Laplace of Si minus A. The inverse of Si minus A. Okay, so we have to, so this was our equation we were using to find our eigenvalues, but now we need to take the inverse, but that's in the Laplace domain. So then we also need to take the inverse Laplace. So let's just focus on what Si minus A inverse is first. So let's just copy what we had here. But this time we're going to set alpha as 2 root 2. So it's going to be equal the inverse of this, where alpha is 2 root 2. So what we do is we take the determinant of the bottom. So that's going to be s plus 2 root 2 plus 2. And then I'm going to switch the diagonal, the primary diagonal, which I did not do. There we go, 2 root 2. And then this is going to be s, and then I'm going to take the negative of the actual diagonal. Now, this thing I'm going to refer to as delta of Si minus A. Because you're going to have to rewrite the whole thing a lot. So it's always good to just name things so you don't have to waste your time writing it over and over again. But I'm going to quickly calculate it. So the determinant of Si minus A is s squared plus 2 root 2s plus 2. And this I can write as s plus root 2 squared. Now, because it's critically damped, I expected it to look something like this, right? I expected it to have two roots that'll be the exact same, and they'll be real. So it's sort of a confirmation that we're on the right track, okay? So then overall, I have phi of s is equal to 1 over s plus root 2 squared. And then I have my inverse matrix, so s plus 2 root 2, 1 minus 2s. Let me just double check that's, yeah, we'll just say it's right. Okay, so that's right. Now, to find the inverse Laplace of this, what most people do is just take the inverse Laplace of that, and that, right? Because they're each a separate term. So you have to sit there and take the inverse Laplace of each of them. But what we notice is that, so let me rewrite it out completely, just to make it very clear. So s plus 2 root 2 over s plus root 2 squared, 1 on s plus root 2 squared, minus 2 on s plus root 2 squared, s on s plus root 2 squared. Okay, so what we notice is that they all look very alike. They have the exact same denominator. So if I can find this one, which is the easiest one, this one is just minus 2 of that, minus 2 times that. This one is just s times that, and s in the frequency domain corresponds to differentiation in the time domain. So I just need to differentiate whatever I find here. Then this one is just a combination of the s I found here plus 2 root 2 of this one. So I really only need to take the Laplace once of the simplest case, right? So what I'm going to do is I'm going to label these as phi 11, phi 12, phi 21, phi 22. Okay? And then what I'll say is phi 12 was the easy one. 1 on 2 plus s plus 2 root 2 squared. And then we want to take the Laplace of this, right? So the inverse Laplace of this, phi 12 of t. So if we go look at our data sheet, so what we have is, again, what we have is not this. So we're close to this one, but we have a scaling, right? We have e to the minus at. So it's 1 on s plus a squared. Okay? So we just have a scaling factor again. So then if I go back to my question, so then I have t e to the minus 2 root 2 t, u of t if you want. Okay, so basically that's the most we'll have to do in terms of taking the Laplace, because then phi 21, so phi 21 of t is equal to minus 2 times phi 12 of t. And we notice that this one is, so phi 22 is just a derivative because it has that s term there. Does that make sense? Is that okay? Any questions? Should it be s plus root 2 squared, not 2 root 2? Yes, you are right. Thank you for pointing that out. So this one I've written incorrectly. So that one should be s plus root 2 squared, because that's what I had above here. Thanks, Nicholas. Minus root 2t. There we go. So it looks like that. Okay. Now, again, phi 22 is just the derivative. Is the derivative of phi 12t. Okay. And then phi 11 is the derivative. So this is the same as this, right? So I'm just going to copy that. So it's just going to be phi 22 of t plus some constant, plus 2 root 2 phi of 12t. Okay? So you just have to really calculate the Laplace once, and then I will give you the final answer. Where is that? Okay, and then the final answer looks like, it's kind of long, 1 plus root 2t e to the minus 2t, te to the minus root 2t, minus 2t e to the minus root 2t, 1 minus root 2t e to the minus root 2t. So just if you wanted to know what the final answer was, that's what it looks like. Okay? Because you just have to work out some derivatives. Okay? Next question. Explain what sort of information we can obtain from this matrix. In other words, what is the purpose of finding the state transition matrix? So the purpose of the state transition matrix is essentially just to tell us, starting from an initial condition, how will my state variables evolve over time? Right? So what is that evolution going to look like for t greater than 0? So my x of t is going to be my state transition matrix multiplied by some initial condition, right? So x of 0. That's what it is, right? Yeah, so it's going to be state transition matrix, which tells me the dynamics of my system and how that will affect an initial condition. And it will be different for every initial condition. So we can just say evolution of, I guess, each state variable over time. Okay, any questions? All good? Cool. Okay, so this one is, okay, so assume alpha equals 1 and the control input signal is given as that, where k is now a gain, is sort of a vector of k1 and k2. So essentially we have a new input and we need to do what I was doing before, but again with a different input. Okay? And one thing that's really, I'll mention is that I think there was a mistake with the marks here. I think this one should be 10 marks. And this one should be, yeah, you can see how many pages I allocated. That one should be 4 marks. Yeah, I was having a look at the marking criteria and I think maybe they made a mention of it, but yeah, that's what I personally think. So yeah, maybe double check with the rash on that one. Okay, so all that's different is now our output looks like this. So what did we have before? We had x of t equals ax of t plus b u of t. One thing I'll actually mention is that this is sort of something you're going to cover later, right? So this is what we refer to as state feedback. So we send the state variables back to the input, and each of them is carried there with a gain, right? So we're targeting each state variable with a gain instead of the whole system. Okay, so but you'll learn about that later. So instead of having u of t, what I have now is that I have plus b minus kx of t plus r of t. So our r of t is what our u of t used to be, right? But now we just sort of have this new factor where our state variables are being carried back with a gain. Okay. So then so I'm going to group all the x of t terms together. So I'll have a minus bk, a minus bk, x of t plus br of t. Not a br of t. Okay, so it's exactly what we had before, except now I have a minus bk. Okay, so instead of a, I have a minus bk, like a feedback. Okay, so then what does it ask for? So exactly what we're doing before, it's asking for the transfer function. So I need to take the Laplace of this. So taking the Laplace, I get s, x of s equals a minus bk, x of s plus b, r of s. And our output is also the same thing. So our output, don't forget, was just y of t equals cx of t. Okay, so now if I also take the Laplace of this, it's y of s equals cx of s. So the goal again is just to take x of s and to sub it in. So rearranging slightly, I get si minus a minus bk x of s equals br of s. And then I just need to take this and I need to move it to the other side. So I'll take the inverse on both sides. So therefore x of s equals si minus a minus bk, the inverse br of s. And then I'm just going to take this thing and sub it in there. Okay, so I'm just going to sub it in. So then I get y of s equals c si minus a minus bk inverse b r of s, but I'm going to put r of s on the other side, right? So I'm just going to divide both sides by r of s. And I can do that because r of s is not a matrix, it's just a input, okay? So we're not done there yet, unfortunately. So now we actually have to apply this equation and we have to find the transfer function, right? So we're given numbers. So I think, what were the numbers? We were given that alpha equals 1. So my C matrix, well, let's just focus on finding this, okay? So SI minus A minus BK, this is equal to S00S minus A minus, what was A? A was 0, 1, minus 2, minus 1. And that's assuming alpha equals 1. And then minus a gain of matrices. And I'm running out of room. Minus a gain of matrices. So that is minus. So K was not a vector. It was sort of a transposed vector. Like that. Right? And then that whole thing. And then our C matrix was 0, 2. Okay, so I'm just working out my B matrix. So SI minus A minus BK. And then when you do this, you get S minus 1, 2 plus 2K1, S plus 1 plus 2K2. Okay, so I'm just skipping the details, but that's essentially what you get. And then, but we're not done yet, right? We want to find the inverse. So what I actually want is the inverse of this. So the inverse, right? Now to find the inverse, so I'm going to give this a name. I'm just going to call this Z again. I can't be bothered writing that every single time, right? So I'm just going to call it Z. And you can do that in an exam as long as you make it clear. Just say equals Z, okay? So then I can say, Z inverse is equal to the determinant. So let's just work out the determinant separately. So the determinant of Z equals, so when you work out the determinant, you get S squared plus 1 plus 2K 2S plus 2, 1 plus K1. Right? So that's just working out the determinant. So that cross multiplied with a minus. And then I also have to flip the terms. But again, I'm not going to sit there and write it out again because eventually I'm going to have to write this again. So I'll just write the answer here, right, to save time. Okay? So then I can say, therefore, Y of S on R of S and is equal to, so my C matrix was 1, 0. And I'm getting the C matrix from what we did at the very, very beginning when I wrote them as a state matrix, okay? 1, 0, and then I have, so I'm going to take the inverse, so I'm going to switch the diagonals, S plus 1 plus 2K2, S, and then I'm going to take the negative of the off diagonal, 1, so that's what, 1 minus 2 plus 2K1, is that 1? Yep, cool. And then I also have, I have to multiply it by B. So that matrix is going to be a 0, 2. Okay. And then you also have a determinant, but the determinant is just a constant. So I'm just going to move it out the side for now. I'm just going to write determinant of Z. It's just a constant, right? Well, it's not a matrix. Now, what you notice is that you have 1 and 2. So you don't need to work out the whole thing. You just need to, when you have it written like this, it essentially picks one value of the matrix. So this one will pick out, a row. So this picks out the first, this one picks out the column, right? So this one will pick out that value there. And then, so it'll pick out this value there, right? So if you do the matrix multiplication, all you care about is this value. Because it's just going to pick out one value, one particular row and one particular column. That too is just a scaling number. So it's just going to be 2 over my determinant, which was S squared plus 1 plus 2K2 S plus 2 1 plus K1. Again, I'm skipping sort of some details, but that's the main gist of it. And we're done. Now, that was a lot of information. So was there any questions? Or did I do such a good job explaining it? I doubt I did, but did I? Thumbs up, thumbs down. Any questions? All good online? We all good? You find it's just the exact same thing we did, what I was doing in the notes before, but just now with that scaled A minus BK. Same exact process. But with little things to keep in mind is that don't keep writing the same thing over and over again, right? Once I sort of calculated the determinant, I didn't need to specifically write out what the inverse is because I'm going to have to go back and write what y and s on R of s is, right? So I've written my answer here instead, my inverse there, right? And I've labeled it as z, so I don't have to write si minus a minus bk every time, okay? Just a few time-saving tips. Now, the next question is sort of like a victory lap. Determine the values of K1 and K2, so the response of the closed system, blah, blah, blah. We've done this a million times, right? This is good. This is like free money. After all our hard work, we deserve it, right? We take this equation. Oh, I meant to grab it. See, that's why I said this one should be 4 marks, right? Because you're just equating I think it was a mistake.
Our one it has it that D was 4 marks and then this one is 5.
Really?
Yeah.
Huh. Because I took this midterm paper from when I did it. Like I had a PDF saved. I'm suspicious of that. Double check with the rash because I don't think it should be worth. I think it should be much more than 4 marks or 5 marks. I think that's kind of harsh.
Yeah, it must be a typo because it doesn't even add up to 30.
Yeah, there we go. Yeah, so then this one's nice and easy, right? I just equate, so K on S squared plus 2 zeta omega ns plus omega n squared. And we've done this, right? And again, you don't have to write the whole transfer function. Well, I didn't write it, I copied it. But in the exam, you don't have to write the whole thing, right? So you just equate this side to that, and you equate that side to that. So I get 1 plus K1 equals omega n squared. 1 plus 2K2 equals 2 zeta omega n. Okay? And then using your formulas, you can find percentage overshoot. So those formulas. I'm going to just give you the numbers for that. So we get, so from the 2% overshoot, we get, so from this, we get a zeta equals 0.779. And then from this one we get omega n equals 5.13. Okay? And then we can just sort of rearrange these equations for K1 and K2. Okay? So like I said, free money, so K1 equals K2. Oh no, not that. K1 equals, so you get 12.16 and K2 equals 3.5. Okay? That's pretty much it. So that was like a bonus 4 marks, or apparently 10 marks. Yeah. Any questions before we move on to the next question? All good? Online? All good? Cool. Okay, let's move on to the next question. We should have enough time. So question 3I was linearization, but no linearization, right? Smiles all around. Next question. So, okay, so this one, so you're given another closed-loop system, but we're asked to find a bunch of things. Now, it's quite a lot of information, so we just tackle it piece by piece, right? So, the first question says, determine the value of Kp such that the output of the closed-loop system reaches 9.035 when a step signal is applied with a magnitude of 10, right? So, basically, this is our YSS. That's our steady state value. Okay. Now note that it hasn't actually asked me to find the transfer function. So if I get a really nasty looking transfer function, I don't have to waste my time simplifying it. I just need to get it to a point where the steady state value can be calculated, right? So I don't need to waste my time. Okay. So as we've been doing, so T of S is just going to be my forward elements. So that'd be GC, G of S over 1 plus GCGH of S, right? And then this is going to be, so KP, so this was just from my loop elements. So that's going to be KP times 10 on S plus 1, S plus 10 over 1 plus KP times 10 on S plus 1, S plus 10, and then I also have 0.2 S plus 1 from H. Now, this one has the most terms on its denominator, so I'm going to multiply the top and bottom with that. Okay. So then this is going to be 10 kp, but I also have to multiply by 0.2. Well, I shouldn't have written it there. Let me write it down here. So that's going to be 10 kp 0.2 s plus 1 over 0.2 s plus 1 plus, oh, the whole thing, right? S plus 1, s plus 10 plus 10 kp. Now, this is a third order. The first thing we notice is that this is third order. So, and it has a 0 on top. So not as nice looking as our previous one. But this is all I need to find the steady state value, right? I don't need to go any further because then the steady state, and also notice that it said with a magnitude of 10, right? So the input is 10 on S. So then I just need to say, okay, so y of S, y of S is equal to lim S approaches 0 of y of S, which is S y of S, the limit. So it's just going to be my input, which I think was labeled as R of S. So R of S times my transfer function, which we'll just call G of S. Oh no, maybe not that. Z of S, right? Just call this Z of S, whatever. Then this thing was 10 on S. So then this will give me the limit of S approaches 0 of my transfer function. So to do this, I just need to set everything with S to 0, which is nice and easy. So that's just 10 kp 1 over 1 times 10 plus 10 kp. And it said ideally that this should equal to 9.035. You rearrange that, you get kp equals, let me find that, 9.36. 9.36. So that's your kp. Okay? That's to achieve the steady state we want. Okay? So find the dominant closed loop poles. If the third closed loop pole is S equals minus 14, when you use the gain kp you obtained from the previous part. Now, again, we had a third order system, and I'm not going to bother rewriting the whole thing. I'm just going to copy this, and I'm going to rewrite it here. Now, we're given that one of the poles is S equals minus 14. Now, we're not given zeta, we're not given any omega n, we're given no requirements on overshoot yet, so we can't go down that path to find where our poles should be. What we can do is we can say that this is going to look like something like S plus 14, and there's going to be some sort of quadratic here. I don't know what it is yet, but it's going to look, it has to look something like this, right? Because one of the poles is given. I don't know if these two other poles are going to be complex, whatever, it doesn't matter. I know that two of the poles have to be that, or one of the poles has to be that. So again, all we're doing is just equating coefficients, okay? So when I expand the left-hand side, what I get is S3 plus 16S squared, and I'm going to use the KP we just derived, plus 65S plus 518 is equal to S3. So now expanding the right-hand side, A plus B plus S, AB plus C, plus AC. And then, like we've always been doing, just equating coefficients. Okay, so from the green one, you can see that 16 equals A plus B, and A is 14, right? So A is 14, so therefore B equals 2. And then you keep going, and then you get C equals 37. Okay, and that's all we need to do, because then what it was asking was for the dominant closed loop poles, right? So, and I have the quadratic here, right? So I have my quadratic, my quadratic is now s squared plus 2s plus 37. And the pole locations are -1 plus or minus j6. Okay? When you're just using the quadratic equation. Now, another method was you could have used long division. I hate long division. I don't know if anyone even remembers it. But you can, should the leading term on the left be 0.2? Possibly. What were you referring to, Nicholas? Which part?
You've got it mnemonic, but there's an 0.2 times s.
It's been divided through. Yeah, so when you divide by 0.2, it's like timesing everything by 5, right? So yeah, so that's been done. I just skipped the details. But you have to actually sit there and unfortunately do that, okay? Does that make sense, Nicholas? All good? Okay, so one thing we'll notice is that A was given to us. If A is not given to you, which is very likely, you'll have to decide where to put A, right? So to do that, we look at our dominant closed loop poles. So our dominant closed loop poles are located somewhere here, right, at -1. Okay, at -1. Now, for it to be classified as dominant, it has to be 10 times greater than the dominant closed loop poles. So then I can just say that at a minimum, my other pole A has to be 10 times my closed loop poles. So it has to be at least -10. So you'd pick -10. That's how you do it if, so this is if A is not given. Okay, moving on. So justify if the closed loop system can be approximated with a second order system, and if so, provide an estimate of the % overshoot and the peak time. So just looking at our system, do we think it can be approximated? Why? Yeah, exactly, right? So one of the poles is -14, and we're looking at the real part, right? What we care about is the real part of the poles, because the real part of the poles is what controls how fast the signal will die out, right? If I have an envelope signal like this, what controls this decay is e to the minus sigma t, right? So how fast the signal will die out is determined by its real part, whereas the imaginary part just dictates the oscillations, okay? So if a pole is all the way over here, so we have e to the minus 14t, which will die off much faster than, say, e to the minus t. Okay? So, yes, real part of closed loop poles is 10 times greater, is 10 times greater than s equals -14. Okay. Technically, it should say real part is probably 10 times less, greater. It doesn't matter. Right? You get the point. Right? It just needs to be 10 times away, right? And it needs to be closer to the origin than the other pole. So maybe 10 times greater is not a good. 10 times less. Let's say 10 times less. Right? Less is a better way of saying it. And if so, provide an estimate of the percentage overshoot and the peak time TP. So again, we're just going to do exactly what we're doing before. So this is our, so what we had was this thing. So this was the closed loop part of our transfer function. This was the closed loop part. And what we're saying is that this can be approximated by s squared plus bs plus c. Right? That's just what we're saying, because we can say we can neglect that s equals -14 pole. And let me just replace these with what they were. I think it was 2s and 37. Right? And now again, we're just going to be sort of like rinse and repeat, equating to our desired characteristic equation. So this thing will be s squared plus 2 zeta omega ns plus omega n squared. So equating that and that, that and that. Right, and again, so now this time we need to provide, so it's like the other way around. We need to find zeta and omega n using the equation we already have. Then we need to do this. Now, in reality, this is not what we do, right? We pick an overshoot we like and a settling time, and then we move the poles around using techniques like root locus and whatnot to do that. But for now, this is the question. So then from our equations. So from the omega n, so you can find omega n equals, where is that? Omega n equals 37 from this one. And then from the green one, you can find that zeta equals, yeah, you're right, root 37, my bad. Thank you. 37, which would be 6.082. And then from this one, you get zeta equals, what does that say? 0.164. And then you can just use the formulas you have. So this one can be, yeah, so there's only one question after this. So then this one gives you percentage overshoot equals, what does that say? 60%, which is quite high. So you can see why we don't pick our poles first. And then this one is, the settling time, 4 seconds. Okay. Any questions with that? All good? Nice. So now this one's a little more interesting, particularly the second part. So the first part says, find the approximated second order transfer function in monic form. What do I have to be careful about when I'm doing this? Yeah, so what I have to worry about is the DC gain, because the DC gain will essentially set where my response stops to, right? So if this is what my initial response looks like, right, it settles to some value here, the second order response might look the exact same, but it'll settle to a different value if my DC gain is different, right? Because when you're working out the steady state value, the numerator is really important. So what I need to do is scroll all the way back up to where my, okay, it's somewhere up, right? So I had, where was it? I had t third equals, so now I'm just going to sub into that transfer function we derived way back. I'm going to sub in the KP we found. So that gives you 93.6 s plus 5 over s3 plus 16s squared plus 65s plus 518. Okay. And now we're approximating this as a second order. So we say approximately, not like that. Approximately, and for now, I'm just going to say some gain k. But that 0 doesn't go anywhere. Okay, and we'll talk about that in a bit. Over, just move this over. So that's, so this, let me just clarify, that's if DC gain is different. Okay. Now, so k on s plus 5, and then we approximated this as s squared plus 2s plus 37, I think, right? And now I just need to calculate the DC gain of this one and this one, because this one is my second order. So then let's do that. So the DC gain of my third order should equal the DC gain of my second order, right? It's a necessary condition because I'm getting rid of a pole, but I want the system to settle to the same value, okay? So when I do that, I get 93.65 over, I think that says 518, must equal to k times 5 over 37. And then from this, we can say that k equals 6.685. 6.685. Okay? So, so we're allowed to go to second order. I just need to make sure it settles to the same value. Okay? Now, that's something else. Okay, so now the next question. Explain if the response of the original system would have the same percentage overshoot and peak time as your estimated ones from the previous part. What do we think? Yes, and so why? Yes, and why?
Work them out using the second order characteristic equation, and they're independent of whatever's on the.
Yeah, exactly. So this is all assuming we have a perfect second order transfer function, not just denominator transfer function. But clearly we've got a 0 lurching on top. So how would it change though? So what do we expect this 0 to do? Let's just for a second plot this out. So if I have, so my poles are at minus there and there, right? So this was -1. And then, so my 0, so let me ask, what if my 0 was located at, say, minus 15? Do we consider it a problem? Why? Kind of. So in this case, we can use the sort of principle of dominance again. It applies to poles and zeros. So we can just say it's 10 times further away. We don't expect it to have too significant of an impact on our system. But in this case, our 0 was at minus 5. So this one's definitely going to cause some trouble. But the harder question is, what type of trouble? How is it going to affect, say, so how is it going to affect percentage overshoot, settling time, and even rise time, which is not asked, but we'll talk about it. So anyone have any guesses? Okay, let's start with overshoot. Do we think it'll increase or decrease?
Decrease.
Decrease? One vote for decrease. So decreasing overshoot would be good, right? It's almost like too good to be true in some senses, right? Because then it's like, why don't I just add zeros to my system? So you're on the right path. What makes you think it'll decrease though?
Because the overshoot around, well, in the same area where overshoot is occurring is where 0 is. It's somewhat close, and so the system will dial as it approaches it.
Yeah. So Hamish is mentioning that because the overshoot, so basically it won't affect. Sorry, say it again.
Because the 0 is in the region where the overshoot is occurring.
So yeah, so he's saying because the 0 is in the region where the overshoot is occurring. So not quite. I'll give you a little hint. Right. So think of. So no, but you're on the right track in sort of thinking in terms of the way you're thinking about it. Recall that. So a 0 is represented by an S, right? Now recall that an S in the Laplace domain is what? What's it? It's a derivative, right? What would a pole be? It's an integral, right? Some sort of integral. Now, what's the difference in how a derivative and an integral approach a change in a signal? So an integral would take into account the history of the signal, right? So if I have some signal, right, rising, so let's just draw out a signal. If I have some signal rising and say we're at this point, it's going to take, sort of a discrete integral, but it's going to take the history of the signal before it provides the next signal. What does the derivative do? Does it take into account the history of the signal? Yeah, so all a derivative cares about is the point it's at and the point that occurred before it, right? So if I have one point here, it cares about y of t minus y of t minus 1 over your delta t, right? That's all the derivative cares about. So when there's a change in the signal, the derivative is going to respond to it very, very aggressively, whereas the integral is a little more conservative because it's taking into account the entire history of the signal, right? So the derivative will be very, very aggressive. So we expect the rise time of the signal to drop. We expect it to be faster than that transient response because that's where the maximum growth is, right? That's where the signal's moving at its fastest speed, right? In that transient region. And a derivative reacts very aggressively to high change, right? The faster the change, the more aggressive and the higher the derivative is, right? So we expect the rise time to decrease, but it almost feels too good to be true. So what's the problem with this? Because why don't I just add 1,000,000 zeros to my system? Unstable? Yeah, exactly. So the overshoot's now going to jump because it doesn't care what's happening beforehand. So it only cares about what happens then and before. So the overshoot, so it's going to be faster, but the overshoot's going to look something like this, right? It won't have much of an effect here in the settling region, purely because there's not much change happening, right? So I've actually plotted the responses on MATLAB, and so the blue one is without a 0. The blue one is the same transfer function with a 0. If we have a look at the overshoot, so initially we had 60%, which is exactly what we calculated, but then it's gone to 100%. I mean, that's quite a jump, right? So from 60% to 100% overshoot. But our rise time has gone from 0.2 seconds to 0.1 seconds. So it's reacting aggressively, but when it comes to that peak, which will occur even without the zero, it reacts too aggressively and it just shoots up, right? The settling time, there's a slight difference, about 0.3 seconds. Not really enough for us to determine sort of a pattern. But yeah, this is what we call a PD controller, right? So a PD controller is used for the transient, to improve the transient, transient response. But it also has pushbacks, so then we combine it with PID, with an integral controller as well, to maximize the benefits of both. And yeah, that was the exam. Was there any last questions anyone had? Anything in the course? Anyone online?
You mentioned how the 0, -5, when it has an integral, it smooths it out. But
oh no, the 1NS was referring to a pole.
oh, okay.
Yep, so it was referring to a pole. What's monic form mean here? Monic form refers to, so if you have 1 on s squared plus bs plus c, so it means you don't have any a term next to the s squared. So it's just a monic term. Okay. Now, there was a lot of questions, and so you'll have about an hour and a half to do this exam. I just really need to emphasize structuring your answers. Like basically on my hands and knees begging you to structure your answers. Because again, you are going to make a mistake. It's inevitable. Okay? And you need to prepare for the fact that you're going to make a mistake, and you need to be able to go back and read your answers. And also don't try moving at 1,000,000 miles per second. It's okay to slow down for a bit. Those 1 to 2 minutes you spend actually reading a question rather than just writing constantly is much more beneficial in the long run. Okay? But yeah, otherwise, good luck. I'm sure you'll do well. I'm not sure if I'll be there, but if I don't see you, yeah, good luck. Any questions online? Yeah, no worries. Cool. Yeah, that's pretty much it. Thanks for coming. I hope you learned something. Hope you had a good time. Thumbs up. We had a good time. Thumbs down. You can be honest. Say thumbs down. All good? Great. Cool. Thanks, guys. Thank you. Nice. Thank you online. Thanks, guys. Thank you. Cool. Yes.
Can I ask a question about the first question?
Yeah, of course. What's up? No worries. See ya, guys. Bye, guys. Good luck with your exam. No worries. See ya. Oh, what's up?
Yeah.
Which question?
First.
Very first question. Oh, you mean this one? This question?
Yeah, yeah. So I want to ask. So
yeah.
I just flip this secondary side to the primary side, and I write the motion equation.
The what?
The motion of the equation.
Yep.
And then can I just, because I flip this theta2 to theta1. So I just one diagram like the JEQ.
Yep. So this one here.
Yeah. So why can I use the theta2 in here?
Because we've reflected to the primary side.
Yeah.
So we don't need to worry about the direction. Like the direction is theta1 because we've moved everything here to here.
Oh, so if I.
So then if you reflect everything to here, then you're theta2.
Oh,
yeah. Okay. Makes sense? Cool. Cool. All good? Tiring? It was quite long, I know. Yeah, cool. I don't think so. I think about an hour and a half. Really? I don't. Maybe, possibly. Yeah, that's true. But it's still a long exam without linearization. You'll be okay. You'll be okay. No worries. No worries. Bye, guys. Yeah, see you Friday.